And welcome back. Now, today we've got a few things to talk about before diving into the details of one of them. First of all, it's this thing over here. In fact, it's this one here, which I don't want to go too close to because you'll see why. If, in fact, I press this green wire here, hello, here I am. Yes, you might have guessed it. This is a touch control unit, and it's actually a CAP1188 breakout board by Sparkfun. What are we going to be using it for, in conjunction with this Leonardo style micro, is to have this to control my videos. So if I press other, well, what will be buttons on here, not button touch pads, you'll see if I press this second one, we should go to our code window. There we are. And if I press my third one, which is this black one down here, that's the same code window but with me in it as well. So I think you get the idea of what's happening on here. So let's go back to the main window. Right. So this touch control unit is going to be built into a little box with some touch pads for the three main views that I use, and then the webcam, that's me, and the picture-in-picture of my workbench. So as you can see, it's even now with these funny little bits of wire all hanging out the back, it's working exactly as I wanted it to. The Leonardo I have here, that's a whole topic in itself. I say a Leonardo, it's a Pro Micro of sorts, which could be a Sparkfun Pro Micro, which comes up and identifies itself as such, or it could be a Leonardo Micro and identifies itself as such. They're not originals. I do have an original one coming, and it'd be interesting to see how that changes. The whole point about these, though, is that they don't have the same USB connection as your standard Uno, because this is a virtual USB device, which means this can talk back to my computer. That's how, when I press these buttons, this micro here is saying send the following shortcut keys back to Windows, and then of course this, what you're looking at here, which is my camera unit, will interpret that as say, you mean switch to that camera or go back to that one. So it's identifies itself as a sort of an HID, human interface device, very easy and simple to use using the keyboard library, but we'll talk about this and this in much more detail when I've moved this on a pace. But today we're going to talk a little bit more about this. Now this unit, this is a standard Arduino clone on the bottom, and I've got this shield plugged in, which you've probably seen from other videos I've done, with a little tiny breadboard in here. Now this breadboard I've now stuck on. It comes with a double-sided pad, but I could have used the solder pads to make it more permanent. Now this unit is connected up to this here. This is a DS18B20, which to lots of you of course will immediately ring a bell as being a temperature unit, but it's a temperature unit using the one-wire system, and the one-wire system works differently to I2C or indeed SPI. It's a sort of proprietary communications protocol, but has now been adopted for lots of different things. So I want to talk a little bit about this because there's been lots of things on the forum about A, fundamentally how do you use it and how simple is it to use, and B, what if I want to monitor not just one vat of beer but 2 vats of beer or 4 vats of beer, or indeed your beehive down the bottom of the garden. And we'll be looking how to do that in some detail. So join me in just a few secs when I get this set up, and we'll talk about that then. And welcome back. Here we are now with the board all set up for the DS18B20 temperature converter. Now it's this little device here. It looks like a transistor, just with 3 prongs coming out of it, but there are lots and lots of transistors inside here. There are 2 ways of determining what the temperature is using this device. One is the easy way, using somebody else's library, which is a bit like plug and playing Lego bricks together, which means you don't really learn much and you just hope to God it works, because when it doesn't, you'll be stuck. And there's the hard way, which is you do all the work, you talk to this device directly so that you understand some of the things that's going on. That's what we're going to do first of all. Now don't get me wrong, the library that's supplied does do a lot of the things and takes the pain out of doing this. However, I've cobbled together a bit of code here, mostly comments than code, and it's quite honestly not that difficult. So if we look at this here, right, first of all we have to get the one wire device in, this one here, okay, so make sure you install that. I think it's standard for Arduino, but if it's not, you can just Google it and download it. Okay, there's the debug window for us. Now, there are options on this device. So what we can say is, what resolution do we want this device to return the temperature? By resolution, I mean, do we want it in whole degrees only? So, you know, and it's degrees centigrade, by the way. If you want Fahrenheit, just do a quick maths conversion. So do we want it in whole degrees, like 20, 21, 22? That's a little bit broad, isn't it, really? But 20.5, 21, 21.5 might be enough for like a room temperature or something like that. You can go down to quarter degrees, 20.25, 20.5, 20.75, or the default, which is 0.0625 resolution. And you might think, oh yeah, I'll have it as high as I possibly can to have it the most accurate. Well, then your program's going to be hanging around for a bit, because it takes 3/4 of a second to convert the temperature on here if you're going to have maximum resolution out of the box. So what most people do, apparently, is to reduce the 12-bit accuracy down to 10-bit, which is 0.25 degree. And let's face it, if you're sticking one of these, a waterproof one of these, into a vat of beer or something, does it really matter if it's 21.25 or 21.3? I don't think so. Even for a room temperature, I don't think it matters that much. So most people set it down to 10-bit resolution, and the conversion is done a lot quicker. Something like 160 milliseconds as opposed to a full 3/4 of a second. So I'll show you how to do that, and you can decide then whether you want the highest or the medium resolution, in fact any other resolution in between. So first thing to do, of course, is to understand what the address of your individual device is. Now, each DS18B20 has a lasered unique 64-bit address in here. How you get that address, I'll show you on a different bit of code, not here. I've run that little bit of code and got the address out for this one. This other one over here that's not connected up at the moment, it's going to be used in another little bit of this video, has a totally different address. Okay, so they aren't unique. You only need 2 wires, and well, you need some sort of power somewhere, but this is running on parasitic power, just a little tiny resistor, and you can probably run 5 of these off that one resistor, but it does take power to do the conversion, not just sitting here, but when you say go, give me the temperature, it takes some power, about 1.5 milliamps. So you've got to make sure that if you're asking all 5, for example, to convert the temperature at that precise instant, that you need 1.5 milliamps through this resistor. Just something to bear in mind. Might be better to do it one at a time, stagger them. Anyway, having got your address, your unique 64-bit address for your device, the sequence is fairly good. You reset everything, you select the device using the address, so we're putting in this 64-bit address, and then there are some, let's say, command codes you can send, or registers as it's like to be known, but I like to call them command codes, that you fire off at this thing, and they're all in the data sheet. Now, data sheets are easy to read. Let's whiz over there and have a look. Here's the data sheet for the DS18B. This one, who's this from? Now this is Maxim. It used to be Dallas Semiconductors, but they were bought out in Maxim in about 2001, so it's now Maxim, but the library we'll be using later on is still called Dallas, would you believe? So down here somewhere, forget all this first bit, that's just the characteristics of the device in terms of electrical, you know, minimum, maximum voltage and so forth. It's 5 volt tolerant, this one though. Now it's worth reading this, actually, all this gubbins here, it's worth reading it because it does tell you quite a bit about how it works. Alarm signaling, for example, you might want that if you're putting in a device into a vat of beer or wine or the beehive down the bottom of your garden. You might only want to know if the temperature exceeds or drops below a certain value, so that you can set the alarm to come on at that temperature, and then your Arduino can just poll for those. It says, give me the temperature of all those units that have an alarm condition, that is, that's gone out the preset temperature range that I've set. So that's useful to know. There's lots more about powering it up and so forth. And somewhere down here, oh yes, this is something we're going to be talking about, this configuration register. That's the resolution, that's how you set the resolution. And, well, there's the configuration register there, it talks about it. Anyway, there's loads of stuff in here, and I would say, look, it's not that difficult. It might look a lot of it, but it's not that complicated. The bits you don't understand, skip. But just understand that at the end of the day, what you're actually doing is just sending a series of commands down the wire to this thing to say, oi, get ready, I'm talking to you, not you over here. I'm talking to you. I want you to do this, do that, do the other. And mainly you'll be saying, I want you to convert the temperature now. Thank you very much. I'll give you a few milliseconds to do that. Right, you, this one here, not that one there, you, I'm going to read your scratch pad memory where you've put that temperature information. Okay? And then you say, right, I'm going to read it. 1, 2, 3. Right, I've read it. I'm going to reset now you, not you. Okay, this unique one. And that's the end of that, really. So let's just whiz through this code because it really is fairly straightforward. So what we're saying here is, initially, what's the resolution we want? Now I'm setting it down to 10 bits, which is this one here. So 3F, so in this little tiny bit here, from here onwards, here down to here, that's optional. If you don't want to set it down to the 10 bits, it comes by default as 12 bits, which is 0.0625 resolution, ridiculous amount. But you may want it for something, who knows what you're using it for. But I'm setting it here just to 10 bits just to show you that it can be done. You can then also, incidentally, write that resolution into EEPROM and then remove this code. Remember to remove this code when you're doing it though, because you don't want to write it to the EEPROM every single time. You've done it once, that's it. It just like comes out of the factory then. Right, then the next thing, this is where the real gubbins is. We're saying, right, you, so we're addressing a particular one, that one there. We're saying, I'm now going to ask you to do the temperature conversion, please. That's how we do it. Now, here it tells you what the resolution is, and we're going to wait a full 1 second. Now we're waiting a full 1 second in case you do choose the full 12 bits. As I say though, for the 0.25, which is the 10 bits, this one here, it probably takes about 160 milliseconds, so it's pretty quick. We need to reset it. Then we need to say, you, I think you're getting the idea now, I'll stop saying it. But we're saying, we're addressing the individual unit, we're saying, look, now this command here, this is all defined in the data sheet that I showed you. BE says, right, I'm reading your scratch pad, which is the bit of memory where you've put that temperature, and you read it, 8 bytes of data, but you only want byte 1 and byte 0, they're the ones that actually contain the temperature, and then we're going to convert it using 2's complement, because remember the temperature could drop below 0, which means the very first bit of the temperature returned, which is the most significant bit, which is data 1, will have its bit set. If it is, then of course we have to flip all the bits to get the actual temperature in negative. So that's what this does here. I'm not going to go into that because quite frankly this is just for demoing, and then we're going to print it. So let's actually see this running. So, and there we go. Now my studio here is 25 degrees it says, and if I put my hands on this device here, let me bring it a bit closer to the camera. So if I touch this, you should see it change in sort of increments of 0.25. There we are, 25.25, should go up 25.5 and 25.75, there it goes. So if I really hold it tight, it might leap in bigger increments than that, 26.5, no. It's always going up in 0.25. In fact, it's sort of slowing down now. I'm obviously not as warm as I think I am. So if I let go, you should see that slowly drop. There it goes. So what you can see here is that it's doing it in 0.25 of a degree increment, because we've said we want 0.25 degree increments here on the resolution. Okay, so the resolution is 10-bit. Now if you do want a higher resolution, 0.065, which is out the box, you can do that. All you've got to do is change this bit here. So we've got 3F in here at the moment. Well, if we change that back to 7F and recompile, off it goes, and done uploading. Right, watch the output window here. Here we are. Now we're seeing all sorts of funny values, look, because this 0.0625 isn't a multiple, and therefore looks a bit odd, doesn't it, really, I think? Don't you think? Well, that's probably why people don't use it, apart from it taking forever to convert to this resolution. It takes forever. So if I just sort of touch this a little bit, as soon as I touch it, look, it changes. So you may need this in your project. You might want the ultimate, but just bear in mind you're paying the price in terms of time. Now you might think, well, this doesn't seem a very good design. If I've got to wait a whole 750 milliseconds to get back that up there full resolution, that sounds like a poor design, really. There's a way around that. At the moment, if I bring this in close to the camera, you'll see this resistor here, that one there. Now that's one resistor that can be used for all of these. So from this point onwards, we could have 2 wires coming off here, and that's all we'd need, because the power is being taken down the signal line, a bit like phantom power on a microphone or electric microphone or something like that. But it's basically 2 wires, even though it's called 1 wire. And so what we could actually do is, rather than using this parasitic power, we can actually supply the voltage to each of these. Then what you can do is say, I'm not supplying parasitic power, I'm giving you the full 5 volts, go and get me the temperature, I'll come back in a little bit and ask you whether it's done. So that's an alternative way of doing it. Some people wouldn't want to do that. If you've got a loop in your code over there that needs to do other stuff as well as getting the temperature from this thing, you might say, fire off the command to 5 of my units, say, go and get me the temperature, I'll come back and just poll every few milliseconds, say, are you done yet? Are you done yet? Are you done yet? And then when they are done, you can then retrieve the values out. Now we haven't done it here in this code because it's demo code and it's difficult to do all that polling and stuff writing it manually, but it does mean that this is a bit more flexible than what you might think. But a lot of people, most people I would say, use this parasitic power, because then if this was now built into a project, you see, you could use a little jack plug, a mono jack plug, and just run it off into your beer vat or your beehive or whatever it is you're doing. The waterproof ones are sort of little tubular cylindrical metal ones with a very long lead on, and you just drop it into your vat of beer or wine or swimming pool or fish pond or whatever it is you're monitoring, and they're totally waterproof and they work just great. But then you wouldn't need that kind of resolution that's currently showing. You basically probably want whole degrees might be enough, or at least certainly quarter degrees, plenty. So there we are, this tiny little bit of code here, which once again is probably, I don't know, what, 50% comments, where I've just tried to explain what's happening, is very simple, and it gives you an idea of how we talk to this. Because when we switch to the library in a minute, all that complexity, if you like, goes away, and all you say is, go and get, thank you very much, the end. It's easy, yes, but it means you haven't understood anything about how to talk to it. And you might want to. If you don't want to, that's great. Go and use the library. I mean, let's face it, we don't look at the decompiled code very often of what goes into the Arduino, do we? And reverse engineer that. We don't care. We use the easy manner of writing stuff like this. So, horses for courses. Now, I'm going to kill this one, stop all this, unplug a couple of things, and bring back the other bit of code I've got ready that shows you how to use the library and how to use more than one device at the same time. Right, here we are again now, ready for our library version of that code. But before we do that, there's 2 things I forgot to mention last time. So if we go back to our code window, first of all, if you're using Windows 10, you will have a calculator like this, and if you choose the programmer version on here, look, you can choose programmer, scientific standard, whatever. Programmer is exceptionally useful in working out all those bytes and things. As you can see, there's one on here that I was working out in binary. So there we are. So if you wanted to find out, for example, what a hexadecimal value was in binary, you just set it to hex, type in some values like 56, and then it gives you back the results in decimal, 86, octal, which I've never used actually, but binary is most certainly used. So just a little hint for you there about using the programmer or calculator. There's that. And secondly, this bit of code here is the scanner. Now I mentioned that I had the address on here previously. I'd written it down and we'd used it in the actual code, hadn't we? How do I get that address? Well, this bit of code here is a scanner. Now this isn't my code because the style is not, this is not my style of coding at all. So this is somebody else who's written this. I must have got it off the internet at some time. So if we run this and upload it, let's have a look, see what happens. Because we've plugged in the unit exactly as we had it before, no changes there at all. And it says, there we are, it's found it. Look, looking for on-wire devices, zonk, and it's found it. And that's as easy as that. I'll put this code, like I always do, at the bottom of the video, so you can use that to discover your one-wire devices. Works for all one-wire devices, not just the temperature ones here. Okay, so there was that. This is the library now from Dallas Semiconductor. They wrote this library. As I say, Maxim took them over in 2001, but it's still called Dallas Temperature. So by putting this in, we can abstract ourselves away from all that register and command codes and all the rest of it, and just say, give me the temperature. So look, forget all this bit up the front, that's just initialization. There we say, look, begin, and then we say, give me the temperatures of all devices that you've found, and print it out, or do what you want to do, and then just a delay so they don't get a zillion a second. So let's just upload this and see what happens then. There we are. Now what it's saying there is, look, sensor 0, 25.44. Now this is probably in full resolution, 12-bit, so it is going to have some funny values. If I hold it, there we are, up it goes, 25.63, 81. So the next thing to ask is to say, well, okay, that's fine. You've got that one temperature, but I've got 3 vats of beer that I'd like to monitor, plus the room temperature if could be. If only we could plug in another temperature sensor into this circuit somehow. And look, I've even got a spare one here. What could we do with this next one to plug it in? Well, how about just plugging it in right alongside the first one, which is something you'll never see done with the semiconductors normally, but there we are, look. 2 of them in line, joined together. Now remember, these have got unique addresses, and these aren't transistors, they're integrated circuits, and they're identified by a unique lasered address, 64-bit address inside each one of these. So that bit of code that was on the window a minute ago should better figure out that we've now got multiple units attached. And let's see what it does. Let's reset this window and restart. Zonk. And now it says, right, there's a first one. That first one at the back here is still working. But what about temperature? What about the second temperature? Sensor 1, as it were, if we're starting from 0. Well, if we look at the code here, it says how many have we got attached, and we've said 1. So what happens if we change that to 2, re-upload that, and off we go. Oh look, sensor 0, sensor 1. And it's doing the pair now. How do we know it's working? Well, if I touch the first one, which is the one at the back, we should see sensor 0 going up. So sensor 1 is 26.5 now. Sensor 0 is 27.44. In fact, perhaps it's the other way around then. This is sensor 1 and that's 0. Let's have a look. Ah yes, it was the other way around. It's the way it enumerated the individual devices. So that's 0 and that's 1. It's just the order in which they're discovered. There we are. So that is also running on the parasitic resistor here. And there have been reports on the forum, they've had up to 5 running on that one resistor. the resistor is in the spec sheet, but it's about, I think this is a 4.7k. You can bring it down a bit, but if you get difficulties, perhaps with long runs, you know, the resistance in the lead or something might give you problems, then you'll need to supply 5 volts and it suddenly becomes a 3-wire operation. Simples, as they say. So that's it, that's what we have to do for this. But I would urge you first of all to use the first bit of code that requires a bit of pain and a bit of work to understand what's going on with these things, and then you'll understand perhaps a bit better what's happening in the library. So that winds it up for the DS18B20 from Dallas, or Maxim now. Hope you enjoyed watching it. Thanks for watching, see you in the next video. I hope you're finding these videos interesting and useful. You can leave comments down below and also click that little button that says subscribe. Okay, thanks for watching and see you in the next video.